Hey, here we are on 5G ballistic pendulum. How amazing is that? So we have a dart and it's launched at an angle phi because we ran out of thetas, and okay, we use theta up above. It's gonna fly up and it's gonna move horizontally. So that's kind of cool. How does it do that? Wow, that's a good trick. And it collides with and sticks to a wooden block of mass. So this is called the ballistic pendulum. This is like this old crime lab type of tool, or if you want to investigate, a gun that shoots, you can shoot the projectile into this ballistic pendulum and do things. So it hits a block. The block then swings up into the air. You can see the block swinging up into the air. It's going to make an angle theta with the vertical as shown. So we're going to sketch a horizontal and vertical velocity versus time from the time the dart is launched to the time it hits the block. So it's got, so this is basically a projectile motion problem. So what is the graph telling us? It's telling us that in the x direction, it's traveling at v cosine theta, which is constant, which makes sense because there is no acceleration in the x direction. Whatever v velocity it had. So I guess this is worth saying again, probably. This is like super critical thing here. All right, when it's launched here, it has a velocity v. And that velocity has components. It's got a vertical component and a horizontal component. The horizontal component is v cosine phi, and that's not going to change because there's no acceleration in the horizontal direction. It would be the same as if you just shot it sideways. It would be that. Well, I mean, it wouldn't be the same velocity, but it would be the same idea that it wouldn't be accelerating in the x direction if you shot it sideways. All right, so then so that's what that graph looks like. It looks like a flat line, right? In the y direction, it's got an initial y velocity, a component. It's got an initial y component, but in the y direction, it slows down because it's being pulled down by gravity. So the acceleration due to gravity is slowing the thing down as it, and then when it hits the block, right before it hits the block, its velocity is all horizontal, so it doesn't have any vertical velocity. Neat trick. Identify the system by circling both the dart and the box with the dotted circle. There it is. And sketch a momentum diagram for the system from just before to just after the dart. So the dart's initial momentum is its mass times its velocity. So it's got 1 unit of mass, and it's got 1, 2, 3, 4, 5, 6, whatever, 7 units of velocity. I think they just made that part up to make it look good. And the block's initial momentum is nothing because it's just hanging there. So it's got a mass of whatever it has. It doesn't really say the relationship between the masses, but it's got more mass than the dart, obviously. So they decided it was 6 times bigger for their graph. So afterwards, the momentum of the system, if this one's momentum is whatever it is, 1, 2, the area here, 1, 2, 3, 4, 5, 6, 7, should be equal to the area here, 1, 2, 3, 4, 5, 6, 7, and it is. And you can see that we have 1 more unit of mass over here than we had here. This has 6 units, now we have 7 units of mass, and now we have 1 unit of velocity because the area of this rectangle has to be equal to the area of that rectangle because the momentum is conserved. All right, in a second experiment, a dart with a greater mass is launched in the same thing, and the dart collides in the same block. And with the angle theta of that dart, swing, increase, decrease, stay the same, and it increases. If the mass is increased and the initial momentum is increased, then the impulse applied to the block is going to be bigger. It's going to make that dart swing higher. And you can pause the video and read the words. Nice. They have some lovely words. H. Carlos and I didn't set the timer. It doesn't matter. I've got to finish this. Carlos and they're designing an experiment to determine the impulse given to a cart as it collides with a barrier. Oh, nice. And writes a procedure below. So we have a dynamics cart. So this is a cart. It's just a big block on wheels. The wheels have pretty low friction, right? And then there's a spring. Oftentimes on my dynamics carts, One cart is just a block on wheels. They come in pairs. One cart is just a wooden piece of wood, of 2x4 basically, on wheels. It spin freely, and that's it. Oh, and there's a plate on one end. And the other cart is just like that, except there's a spring sticking out the back end of it. So there's a squishy spring that you can smush. And so there's a force sensor, there's a ring stand, there's the cart, there's a cardboard target. So the purpose of the cardboard target is so the motion detector can see the cart, because you have to have a nice big target for the motion detector. We talked about motion detectors before. They send out an ultrasonic signal, and they need to bounce off of something, so you need to make sure you have a big target for them to bounce off of. And so there they have it. There's their experiment. And here's their procedure. Edit the procedure for length and clarity, and rewrite the new sentences if necessary. So basically, the people here have the procedure and they're cleaning it up. So I would really take the time to read through this. And this is starting to give you an idea. You should have practiced it and then look at yours and look at this one and see how you're doing, because you will definitely get a question on the AP exam, or and on the final exams. You know, I'm hoping that we're together again in real life before the end of the year. And if that's true, then we will have a more traditional type of end-of-course assessment that would involve pieces of paper. And if that were true, then it would be practical for me to give you questions like this and see what you learned. All right? So just be forewarned, you should be practicing and not just copying. Here I saw that I've already graded 2 of these, and I was like, oh, that's interesting. And they both got it right. I don't know if that's because they looked it up or they understood what they were doing. So sketch a graph of what the velocities, function, time, and force would look like for time just before to just after the collision. Yeah, well, that makes sense. So it's got momentum before. So here it has, it's got velocity before, and boom, then it hits the thing and bounces off and goes the other way, right? It's bouncing. Boom. Here, the force is 0, and then this is the force during the collision. Boom. It's pushing it the other way, so it's got a negative force. So this is a typical impulse curve, a real impulse curve. They usually don't look like rectangles, unfortunately. They usually look like this. So if we did this experiment, this is exactly what it would look like. It would just be this dip, right? And the area of this dip would be equal to the impulse. Of course, it would be calculus, really. You could estimate it just by counting boxes and estimating the pieces of the fractional boxes. But calculus is the math used to determine the areas of things that aren't straight lines, that are curvy, is the math of calculus, which I'm so rusty on. It's just, might as well have, I mean, at least I know what calculus is, but it has literally been 30 years. So explain how the representations can be used to determine the impulse. So please read I just explained it. And that's it for this week. We will go on to I next time.